Hello and welcome to this mathematical ramblings video. Today we're going to be having a look at the shape here. You probably recognise it and you might have heard of it. It's the Koch Snowflake, a fractal invented by Swedish mathematician Helge von Koch. Now, as a fractal, it shows some interesting properties like self-similarity. Now this isn't true of all fractals, but it's sort of just a subclass of fractals which shows self-similarity. And also, it shows a finite area, but despite having a finite area, it somehow has an infinite perimeter. And I'll have a look at how this is possible and also how we can link these properties throughout the course of the video. So of course, to start off with, we need to look at what exactly the Koch Snowflake is and how we get to it. So the Koch Snowflake is the result of an iterative process. That means we go through a series of steps and we actually continue them on infinitely to get to the Koch Snowflake. So for the first iteration, we simply start with an equilateral triangle. Now for iteration 2, we add a smaller equilateral triangle along each side, and the length of it is such that it's a third of the original equilateral triangle's length. So if the original equilateral triangle had length k, the new small one has length k over 3. And also the result of this is that all these lines are still the same length, they're all k over 3, all the line lengths. Then for iteration 3, we add even smaller equilateral triangles onto each side, and these will have length k over 9, so you can see each time we're dividing by 3 to get to the next triangle's length. And then iteration 4, they're going to have length k over 27, k over 81, a tiny bit there in the top left of the triangle, and then continuing on. And you can see as we go through these iterations, we start to build up more and more detail. And if we remove all these sort of construction lines, we can see that's actually starting to look like the actual Koch Snowflake. But in reality, the Koch Snowflake is the infinite iteration of this process. Iteration 6 isn't the Koch Snowflake, but if you could continue this process infinitely, then you would get the Koch Snowflake, and that's when it starts to show properties like self-similarity, and of course the infinite perimeter as well. Now, interesting enough, you can also link the Koch Snowflake with the Coastline Paradox. What exactly is that? Well, here you probably recognise it, this is the coast of the UK. But if you look up in the top, according to the CIA fact book, the length of the UK coastline is around 12,500 kilometres. But according to the World Resources Institute, it's around 20,000 kilometres. And you're probably thinking, how can that be possible? Did one of them get it wrong? Because they're both measuring exactly the same coastline. Well, that's where the problem lies, because what's probably happened is that they've used different degrees of coarseness in their measurement. What do I mean by that? Well, if you use a longer length of measurement, for example, you measure each kilometre of coastline, then you're going to get a shorter length for the overall coastline. I'll explain it with this example. So let's say you have, this is just sort of a random coastline, it's not an actual coastline of course, you have this coastline here. You could take the measurement just to be the distance between the furthest points. So let's say that could be something like 10 kilometers, for example. Or you could make it a little finer, your degree of measurement. You could pick a point in the middle because it's not a flat line. And that could be, the length between the points can now be 6 kilometers, so a total overall of 12 kilometers. So you can see here how using a finer degree of measurement actually increases the measured length of coastline. And by continuing to decrease the length of measurement or increase the fineness, then we're actually going to end up getting an increasingly larger result and value for the coastline measurement. And actually, in the same sense that the fractal can have an infinite perimeter, the coastline can have a theoretically infinite perimeter if you continue to decrease the measurement. And that actually results in some problems, because what's the best way to measure a country's coastline? It's difficult to compare coastlines if any coastline could have a length going up to infinity. But anyway, if you're interested in learning more about this topic, I highly recommend some videos on YouTube. There's this one by Real Life Law, but there are loads of other good ones by maths YouTubers like Numberphile or 3 Blue 1 Brown. I'll link them in the description, and I also put a card up in the top right if you're interested in learning more. So now let's see if we can go about showing why the Koch Snowflake has a finite area, because you might think, given that you're adding an infinite number of triangles throughout the iterations, that maybe it'd have an infinite area. but we can go about showing why exactly this is not the case. We'll start off simply with iteration 1 because this is just a simple starting point, and to keep things simple, we can say that the initial equilateral triangle has an area of 1. So A1 equals 1. I'm using A subscript 1 here to mean the area of iteration 1, and etc. Then for iteration 2, we're adding on 3 small equilateral triangles. And they're actually similar, meaning that they're just shrunken down versions of the original triangle, and because of that we can use scale factors. If we say that the length of the larger equilateral triangle is k, then we know that the length of the small equilateral triangle is k over 3, and as such the area will be 1 over 9, because we're squaring the 1 over 3 to get 1 over 9. And so adding up the areas of all these triangles, we get A2 is equal to 1 plus 3 times a ninth. And that simplifies down to 1 and a third, or just 4/3 if you want. Then for iteration 3, we're adding on even smaller triangles, but all of these are all still just shrunken down versions of the original triangle. So they're still similar, and their lengths are k over 9 compared to the original of just k, and so the areas will be 1 over 81 because we have 1 over 9 squared. And adding up all these areas again, we get to simply 1 and 30/27, or just 40 over 27 if you prefer improper fractions. And we could continue going like this, and there is actually a pattern, and you can even work out the area of the infinite iteration using sigma notation, but there's a much neater way to do it using the property of self-similarity that the Koch Snowflake exhibits once it's actually on its infinite iteration. So we can look at that now. If we look at this, if you look at just the top part of the Koch Snowflake at the moment, in blue and red, that's actually called a Koch curve. So a Koch curve is a single side of the Koch Snowflake. Now, you can see here, we just zoomed in the red, and now it's what was previously blue, which means that the Koch curve is actually self-similar. And that's useful because it lets us use scale factors once again. If we call the area of the entire Koch curve, of that red Koch curve, A1, and also R, and then we can look at a small section of that curve, so this part highlighted in blue, we can actually work out the area of the blue part in terms of the entire part. So we know that the length of the larger red Koch curve is k, and the length of the smaller section of the Koch curve is k over 3. And because they're self-similar, then the area is going to be r over 9. It's going to be a ninth, because we have 1 over 3 squared, which is 1 over 9, so r over 9. And that's useful because what we can now do is write A1 in terms of A2. Or to be precise, we can say that A1 is equal to 4A2 plus a ninth. Where exactly does this come from? Well, if you look in the bottom left, the red Koch curve, so all of A1, is made up of 4 of the smaller Koch curves highlighted in blue, plus the big equilateral triangle at the centre, which we know has an area of ninth, just from iteration 2. And we can now substitute our values for A1 and A2 in terms of r, giving us r equals 4r over 9 plus a ninth, and then we can just manipulate this to eventually get r equals 0.2. And that's just the area of a single Koch curve. We actually have 3 Koch curves, one of each side of the equilateral triangle, and the equilateral triangle itself. So you can say that the area is equal to 3r plus 1, because the area of the equilateral triangle is 1. And substituting our value of r as 0.2 into this, we get that the area is 1.6. And that's not even double the initial equilateral triangle's area, so it's very much finite. And now finally, let's look at proving that the Koch Snowflake has an infinite perimeter, despite its finite area. So again, we'll start off with a base case with iteration 1. But this time, instead of saying that the area of the triangle is 1, we're going to say that the side lengths are 1. And then, so as a result, the perimeter is just going to be simply 3 times 1, which is just 3. And this time I'm going to use p subscript 1 to mean the perimeter of iteration 1, and etc. Then for iteration 2, we have sides of length a third, and we actually have 12 sides. So we multiply those together, and we'll get p2 being equal to 4. Then for iteration 3, we have side lengths of a ninth, so you can see each time the side lengths are being divided by 3, and 48 sides. Then we multiply these two together to get 48 times a ninth equals 5/3. And then iteration 4, we have side lengths of a 27th and 192 sides. So you can see the number of sides goes up quite quickly. And as we have a length of 1 over 27, you can multiply these together to get P4 being equal to 7/9. And you can probably also see a pattern here with the side numbers, but we'll just go and see what we know so far. So if we consider what we know so far, we know we have side lengths of 3, 12, 48 and 192, iteration 1 to 4 respectively. Then we have 1, a third, and 9th and 27th in terms of side length. And to get the perimeter for these, we just multiply them together. So that will come naturally if we can get an nth term for the rest of them. Now, if we consider the nth term, how many sides will there be? Well, you might actually notice a pattern here, because 3, 12, 48, 192 is actually just a geometric sequence. We've got times 4 for each time. So we're going to have a geometric sequence, the nth term is 4 to the n, and we might have a coefficient in front. Now in this case we don't start with 4, so we have to start multiplied by 3/4 such that we start with 3. And then for the length, this is a pattern that's easier to see, but each time we're dividing by 3. And as a result, we again have a geometric sequence where we have dividing by 3 to the n, or in other words, you're timesing by 1/3 to the n, because timesing by a third and dividing by 3 are exactly the same. Now we don't start at a third, so we have to multiply by 3 so that we start at 1 with this geometric sequence. And now finally, if we want to obtain the perimeter, all we have to do is multiply these together, such that we have 9/4 and this being multiplied by 4 over 3 to the power of n. And now we can quite easily consider what happens for iteration infinity, the limit for infinity. So we can say this, because we know that p of n is 9/4 times 4 over 3 to the n, that means that the limit as n goes to infinity of p of n is equal to infinity, or in other words, infinite perimeter, and the perimeter diverges. But why exactly is this? Well, you need to focus on this 4 over 3 to the n term. This diverges. That means it goes to infinity because 4 over 3 is larger than 1. And more generally, a to the n diverges to positive infinity for a larger than 1. And the reason for this, if you think about it, is that if you're multiplying by a number larger than 1, then the number is going to be constantly increasing by greater and greater amounts. Sort of an exponential function. So the exponential function goes to infinity. So that's why it actually has an infinite perimeter for the nth iteration, whilst the area actually remains bounded and the area converges to 1.6. So I hope you enjoy this video. As I said before, if you're interested in learning more about the Coastline Paradox, I'll link some videos in the description and I'll put a card up in the top right. I highly recommend those if you're interested in it. And beyond that, please like, comment and subscribe. Any advice, any suggestions would be greatly appreciated. And have a good one.